Hello, everyone, and welcome. Today, we're tackling a crucial topic in software development: load testing. Think of it like a meticulous engineering process. Instead of waiting for a bridge to collapse under real traffic, you proactively drive increasingly heavy trucks across it, pushing its limits to find weaknesses. That's precisely what we aim to do with our quiz platform. Our core mission is to simulate thousands of concurrent users interacting with our systems simultaneously. Why? To find its breaking points before real users ever encounter them, ensuring a seamless experience for everyone. This practice is especially crucial for high-volume and AI-driven platforms. Consider the lessons learned during events like the COVID lockdowns, where platforms like Netflix struggled under unprecedented demand. The sobering reality is that most systems fail not from simple bugs, but from sheer volume. Your sophisticated AI recommendation engine might perform flawlessly for a single user, but what happens when it needs to process thousands of requests concurrently? Load testing helps us prevent those catastrophic failures, making sure our platforms are robust, scalable, and ready for any challenge. Now, let's look at how we actually execute this. Our sophisticated load testing ecosystem isn't a single tool, but rather three distinct yet highly orchestrated layers working in unison. First, we have the load generation layer. This is where the magic of simulating real-world traffic happens. Instead of just firing random API calls, tools like Locust is LOCUST, allow us to script and simulate realistic user journeys, from selecting a quiz to answering questions, and finally, processing results. This ensures our tests accurately reflect how users truly interact with the platform. Next, we move to the monitoring layer. This is our mission control center. Here, real-time dashboards track an array of critical performance metrics: response times, error rates, CPU usage, memory consumption, and even database connection pools. This layer provides immediate visibility into how our system is behaving under stress. Finally, the analysis layer takes all that raw data and turns it into actionable insights. Python scripts automatically detect performance degradation patterns and are configured to trigger alerts when predefined thresholds are breached. Together, these three layers give us a comprehensive, proactive, and intelligent way to understand and improve our system's performance. One of the most critical differentiators of effective load testing is moving beyond simplistic random requests. Our core concept revolves around realistic load simulation, meaning we mirror actual student behavior, not just arbitrary API calls. What does this look like in practice? We break down the user experience into distinct phases. First, there's the quiz discovery phase. This is when students browse available quizzes, which primarily stresses our database with numerous read operations. Then we enter the active quiz phase, characterized by rapid-fire question answering and real-time state management, demanding efficient backend processing and network communication. Following that, we have the AI processing phase, where our system makes calls to services like the Gemini API for dynamic question generation or feedback, introducing unpredictable processing delays. And finally, the results phase, where scores are calculated and leaderboards are updated, often leading to database write bottlenecks. Each of these phases stresses different system components in unique ways, and by simulating them accurately, we gain a much deeper understanding of our platform's true performance characteristics under varied conditions. Once we understand how our system behaves under realistic load, we follow a clear, predictable pattern for optimization. This is our performance optimization pipeline. It begins with baseline measurement. Before any heavy testing, we establish current performance metrics under normal operating conditions. This gives us a crucial reference point for comparison. Next comes load injection. Here we gradually increase the number of concurrent users while meticulously monitoring all system behavior. This controlled escalation helps us observe how the system degrades as stress increases. The most critical step is bottleneck detection. This is where we pinpoint the weakest link in our entire architecture. Is it a slow database query, an inefficient API endpoint, insufficient memory, or an overloaded CPU? Identifying the precise point of failure is key. Once detected, we move to targeted optimization. We apply specific fixes, such as implementing caching strategies, optimizing database connection pools, or refining inefficient code. And finally, validation. We retest the system to confirm that our optimizations have indeed improved performance and haven't introduced new issues. It's important to remember that quiz platforms have unique performance patterns. Think about exam periods with 10 times traffic spikes or synchronized answer submissions causing database write bottlenecks. This pipeline helps us tackle those real-world challenges systematically. So, how do we bring all this to life? Our implementation strategy centers around using Locust as our primary tool. Its Python-native approach allows us to write highly flexible and realistic user simulation scripts, modeling actual student behavior, not just artificial load. For immediate visibility, we'll integrate custom real-time monitoring dashboards. These will display critical metrics alongside our load tests, giving instant feedback on system behavior under stress. We'll also implement automated bottleneck detection using Python analyzers. These scripts will constantly watch for performance degradation patterns and automatically flag components needing attention, providing you with truly actionable insights. By the end of this lesson, you'll have a robust load testing suite. Now, for your assignment, I challenge you to become a performance detective. Your mission is to design a load testing scenario that discovers your system's actual breaking point. You'll need to simulate realistic user behavior, test AI integration under load, identify your top 3 performance bottlenecks, and implement at least one optimization. Start small, gradually increase load, document your findings, and remember, the bottleneck is usually not where you expect. Database connection pools often max out before CPU or memory limits are met. Good luck!